let's discuss the Fundamental Theorem of Calculus, Part 1. So if our function little f of x is continuous on a closed interval from a to b, and we're going to define a new function, capital F of x. So this new function, capital F of x, is defined as follows. We are going to basically define capital F of x to be the integral from a to x f of t dt. So this is the function that we described in the warm-up video earlier. So just as a reminder, our independent variable is x, and the upper limit of integration is also going to be x. And we're basically going to integrate the function little f from a to x. So the output of this function is going to be the area under a curve. Okay? So what does this theorem tells us? Well, this is an if-then statement. So it says if all of this stuff is true, okay, then this following conclusion is true. And the conclusion is that f prime of x is equal to little f of x. So I'm going to highlight the conclusion of this theorem. And let's unpack this a little bit. So basically what the fundamental theorem of calculus says is if you start with your little function f of x, and then you create this integration function, when you take the derivative of the integration function, you just get the original function back. Okay, so this is kind of amazing. So let me write that up. If you start with a function you find the integral and then you take the derivative, you get your original function back. So this basically says that integration and differentiation are inverse processes. Okay, differentiation and integration are inverse processes. It's basically saying that differentiation will undo integration. So that's kind of amazing. And I want to prove this theorem for you. So we know enough to prove this theorem, so let's do it. All right. The conclusion involves the derivative of capital F. So I'm gonna have f prime of x, capital F prime. And I'm going to use the definition of the derivative. So the definition of the derivative is you need the limit as h goes to 0 of capital F of x plus h minus capital F of x, all divided by h, like so. Okay? And we can write out what each of those pieces are. So I'm going to write this as the limit as h goes to 0. Instead of dividing by h, I'm going to multiply by 1 over h. That's just going to make the writing a little bit easier. And when I go and I write what capital F of x plus h is, that's just going to be the integral from a to x plus h of f of t dt, like that. And when I write out what capital F of x is, that's just the integral from a to x of f of t dt, like so. Okay. So in our next line, what we're going to do is I want to invert these limits of integration in our second integral. And we know that when we invert those limits of integration, you're going to pick up an additional negative sign. So let's write out the next step here. So this is going to be equal to the limit as h goes to 0. You got 1 over h, the integral from a to x plus h, f of t dt. We had the negative sign there originally. We pick up an additional negative sign when I invert these limits of integration. And as we all know, a negative times a negative results in a positive. Okay? All right, cool. The next thing that we want to do is we really want to notice that I have the same lower limit of integration for the first integral as upper limit of integration for the second integral. So in the next line of my proof, I am going to simplify the things inside the square bracket, and that is going to just become the integral from x to x plus h f of t dt, like so. Okay, so I believe this was property 6 in the 4.2 section. We're integrating from x to a and then going from a to x plus h. So that's the same thing as just going from x to x plus h. All right, awesome. So what I'm going to do next is recognize that this denominator right here, this h, is really the same as x plus h minus x, right? In other words, I have x plus h. If I subtract x, the result I get is h. So this whole integral right here, this integral is really, the right-hand side is the average value of f from, or let's say on, the interval x comma x plus h, right? So what this means is that this is equal to f of c for some c in the interval x plus h. And this is true by the mean value theorem for integrals. Okay, great. Now here is where we use the fact that our little f is going to be continuous. Okay, so since f is continuous, this means the limit as h goes to 0 of f of c is equal to the limit as c gets closer and closer to x of f of c, and that is equal to f of x. All right, so at the end of all of this, we've come to the conclusion that the derivative of capital F of x is equal to lowercase f of x. And this concludes our theorem. So I feel compelled to go back up to the top here and highlight the fact that little f is continuous, because that was pretty important for our proof at the very last step there. All right, everyone, we will definitely look at a lot of examples of using this theorem in class. I don't really need you to memorize the proof. I just wanted to show you the proof, since we learned all the different pieces, the definition of the derivative, the mean value theorem for integrals, continuity. It all kind of came into the proof of this very important and fundamental theorem. Take care, everyone.